Hey everybody, my name is Bong and I'm your reporter for today. In this video, we're gonna discuss the concepts and some examples of complex line integrals. So complex line integrals really aren't that much different from real line integrals, which was discussed by Ma'am Ruth. In that, we pretty much evaluate them by parameterizing, but the only real difference is that we're now in the complex plane. So we have the imaginary line or imaginary unit I possibly floating around somewhere, but it really doesn't change a whole lot. So it's just a pretty much a different way of viewing the same thing actually. So to learn and understand more about the line integrals and its visual presentation, I'll have a card up in the top. Check that little info button at the end of this video and to check how to differentiate complex and real line integrals. For complex line integrals, it is convenient to know the ingredients in order for us to define how the line integral works. So for the first one, we have this z is equal to x plus I times y, which is our complex plane. And then we have this dz is equal to dx plus I dy, which is our complex differential. And then we have gamma of t is equal to x of t plus I y of t, which is our curve in a complex plane. And then we have f of z is equal to u of xy plus I v of xy, which is our complex function. Okay, so suppose we have this notation dz is equal to dx plus I dy. And given a complex valued function on a curve gamma, which is our h of z, then it implies that by the definition of line integral, then the integral of h of z dz under the curve gamma is equal to the integral of h of z dx under the curve gamma plus I times the integral of h of z dy under the curve gamma. And then if this gamma will be parameterized by the z of t is equal to x of t plus I y of t, where t is greater than or equal to a but less than or equal to b, then also we can rewrite this h of z dz under the curve gamma is equal to h of z times dx plus I dy under the curve gamma, because dz is equal to dx plus I dy. Then by using that parameterization, we can have this one as the summation of h of z j times x j plus 1 minus x j plus I times summation of h of z j times y of j plus 1 minus y of j. And if this z of j is equal to x of j plus I times y of j, then we can conclude that the integral of h of z times h of z dz under the curve gamma is equal to the summation of h of z sub j times z sub j plus 1 minus z sub j. We can also define complex line integral by using a function that is continuous on a directed smooth curve gamma. And note here that the smooth curve is simply a curve that do not cross itself and have no sharp corners. And if now we are able to find some parameterization of gamma, then we know that the integral of a function f along the curve gamma is equal to the following. And in this expression, we have the z of t is our parameterization of the curve gamma, and a and b are the constants for the starting and end point of our variable t. The next thing I would like to touch on is why is the path gamma so important? Why do we need to know how we go from one point to another? In the old good old days, when we only need one axis to describe our input variables, we know that the only way to go from one point to another was in a straight line. But here, in complex analysis, we need two axes to describe our input variables. So for example, we have z1 to z2, then we need two axes. Then this means that we are no longer limited to only one path. We could, for example, follow this path here, but it is also completely fine to follow this path here. But yeah, this path, since the only criteria I have is that I go from the starting point and end point, which I can do an infinite amount of ways. And this is why it is important to know what kind of path you're taking from starting point and end point, since different path in general gives different answers. Another good thing to know is some standard parameterization. So if you, for example, you'd like to parameterize the straight line goes from z1 to z2, then we have that the parameterization is going to be z of t is equal to z sub 1 plus t times z sub 2 minus z sub 1. You will get the starting point, and if you insert t is equal to 1, you will get the endpoint. And the reason we do this is to preserve a direction of curve. And in general, when doing these kinds of parameterization, you always want to have that lower bound of t inserted into the function that will give you the starting point, and that upper bound of t is inserted into the function that will give you the endpoint. This way, you will always be able to preserve a direction of curve. So if instead you will using a path in a circle, then we have that we have this circle with the center of z sub 0. Then our parameterization is going to be equal to z0, which simply is the center of the circle, plus r, which is the radius, times e raised to the power of I times t, where t is greater than or equal to 0 but less than or equal to 2 pi. Since we will like to go for the complete lap around the circle, but let's say for example that you would only like to go half a lap around the circle, then we will need to change our upper bound limit for t to pi instead of 2 pi. And some other good things to know is that if you would like to determine the integral of a function f plus a function g of some path gamma, then we can split them up and the term for integrals for f and g separately. Let's have our first example. So here we want to evaluate the integral from 0 to 1 plus I z squared dz. So from 0 to 1 plus I, we can just think of that as the straight line path between the point 0 and the point 1 plus I. And if we consider the complex plane, 0 is still just the origin. So we have this value x, or this x-axis, and this y as our horizontal axis. So here, 0 at the origin and then 1 plus I is really the point 1, 1, or the ordered pair 1, 1. The reason for that is that 1 plus I is just the same as 1 plus 1i, and then this 1 represent as the x value, and this 1 represent as our y value. So if we were to plot this point in the complex plane, we will get this point here. So basically we're integrating a sort along this path. So along this path, this pink arrow of this line from 0 to 1 plus I. So the arrow indicates the direction. So we go from 0 to 1, plus I, and we're integrating along this path of this line here. So we have a complex line integral. So what we want to do is just kind of parameterize this path. Okay? So remember, we have z is equal to x plus I y. And if z is a function of t, then it implies that, it implies that x and y are both function of t. So x of t plus I y of t. Okay, then what we can do is look at our path here, okay, and see, okay, what kind of path do we have? Well, we just have a straight line, right, that basically goes from 0 to 1. Okay, so 0 to 1. So there are many different ways we can parameterize that, but perhaps the best or simplest one is going to be, let's just say, x of t is equal to t and y of t is equal to t, where our t is greater than or equal to 0 but less than or equal to 1. And we know that z is equal to x plus iy, or z of t is equal to x of t plus I y of t. So if we sub these values, then we can get z of t is equal to t plus ti. Okay? And then if we squared both sides of the equation or the equality, so we have z squared is equal to t plus ti squared, which is equal to t squared times 1 plus I squared. Okay? So let's go back to the problem. So our problem is the integral of z squared dz from 0 to 1 plus I. And since from the complex plane, we get that our values will have interval of 0 to 1. So we can rewrite this one as the integral of z squared dz from 0 to 1, right? And then this z squared is the same as t squared times 1 plus I quantity squared, right? So we will have t squared times 1 plus I squared from 0 to 1 dz, no? But our function here, our variables are all t, no? Mga t siya tanan. So therefore, we need to change dz into function t, no? Or derivative with respect to t. So how will we do that? So let's use this equation. Okay? So z of t is equal to t plus ti. So if we derive z of t, we can get dz is equal to, dz is equal to 1 plus I of dt. Right? Tama? So, since dz is equal to 1 plus I dt, so therefore, if i-sub natin siya diri sa atong function, then, o sa atong given, then we will have 1 plus I times dt. Okay? Then, combine like terms. So, we will have the integral of t squared times 1 plus I cube dt from 0 to 1. Okay? But since 1 plus I is a constant, so let's put that one outside sa integral sign. So we'll have 1 plus I cube times the integral of t squared dt from 0 to 1. Okay? So let's integrate t squared from 0 to 1. So we'll have 1 plus I cube times 1 or t 1 over or t cube over 3 from 0 to 1. Okay, so it implies that we have 1 plus I cube times 1/3. So therefore, our integral of z squared dz from 0 to 1 plus I is just equal to 1 plus I cube over 3. Okay, so let's have another example. So we are tasked to evaluate the integral of z dz under the curve gamma. So we always start by parameterize the path, and in the first example or the second example, we have the path is a line, and therefore should be using the parameterization here with z1 as minus I. But first, if you want to solve a complex line integral, you need first to write the formula or the definition of complex line integrals. So we have the integral of fz or h of z dz under the curve gamma is equal to the integral of f of z of t then times z prime of t dt from a to b. So first, let's solve this expression. Okay, so to solve that expression, so we need the formula of parameterization in the previous slide. So we will have z of t is equal to z sub 1 plus t times z sub 2 minus z sub 1. Then, because our path or our direction is from negative I to 2 plus I, then our z sub 1 is equal to negative 1, and then our z sub 2 is equal to 2 plus I. So let's sub that values here in our equation. So we have z sub 1 is equal to negative I plus t times z sub 2 is equal to 2 plus I minus I. Okay? Notice that if you combine like terms here, so we will have negative I plus t times 2, negative, 2 plus 2I. Okay? Where our t is greater than or equal to 0 but less than or equal to 1. Okay? So, so next is we need to solve this expression, okay, for us to use this formula. Okay, so for that we will have z prime t, which is equal to the derivative of negative I, then plus t times 2 plus 2I. Then negative I is a constant, so 0 na siya dyan. Then 0 plus the derivative of t or 2t is equal to 2 plus the derivative of 2it is equal to 2I. So therefore, the z prime of t is equal to 2 plus 2I. Okay? So next step will be to use the definition of complex line integral to solve the problem. So we have the integral of z dz under the curve gamma is equal to the integral of z of t times z prime of t dt from a to b. Okay, so our a to b is equal to 0 to 1, right? Then our z of t is equal to negative I plus t times 2 plus 2i, then times 2 plus 2i. Okay, then don't forget to write dt. So multiply, no, we use multiplication, so we'll have the integral of negative 2i plus 2 plus t times 8i dt. Okay, then integrate that from 0 to 1, then we will have t times negative 2i plus 2 plus t squared times 4i. Then integrate that one from 0 to 1, which is equal to negative 2i plus 2 plus 4i minus 0 plus 0, which is equal to 2i plus 2. In our next example, we have the same parameterization and the same start and end points, but this time we're going along a different path. So this time we're going along this quarter of a circle, which is centered at I, then with a radius of 2. So, and this information give us the following parameterization. And the hard part here is really to determine the values for the upper and lower limits of the t value. The way I think about it is that the following, we're starting at the minus I, and that is the down point of this circle, this one. So usually the down part of the circles is always 3 pi over 2. And then we go to the right point of the same circle, which is 2 plus I. In this case here, and that point will always have the angle, no? Always have the angle 2 pi, which is, in other words, 0. Okay? So we know that our interval, or our upper and lower limit, is 3 pi over 2 and 0. So therefore, we have t is greater than or equal to 3 pi over 2, but less than or equal to 0. But before we solve that, let's write the definition of, or the formula in solving the complex line integrals. So we have the integral of f of z dz under the curve gamma is equal to the integral of f of z of t times z prime of t dt under the interval a to b. So first, let's solve this expression, and next one will solve the z prime of t. So for f of z of t, we will use the previous table, which is the parameterization of the circle, right? So we have z of t is equal to z sub o plus r e to the power of I t, right? Then our z sub o is equal to negative I, right? So we have negative I know z sub o is our center of the circle. So therefore, our z sub o is this one, I. So we have I plus the radius, which is 2, no, 2 times e to the power of I t. Okay, so remember, our t is greater than or equal to 3 pi over 2 but less than or equal to 0. Okay, so we have z of t is equal to 1 I plus 2e I 2e to the power of I t. So next expression will be this z prime of t dt. So we'll have z prime of t is equal to the derivative of I with respect to t is equal to 0 plus the derivative of 2a to the power of it is equal to e to the power of it then times 2 then times the derivative of it, which with respect to t is equal to I. Okay, so therefore our derivative of z of t is equal to 2i e to the power of I t. Okay, so by substituting these values, the z of t and z prime of t in our equation or in our formula, then we can solve this integral of z dz under the curve gamma. Okay, so we have the integral of z dz under the curve gamma is equal to I plus 2e I to the power of t times the z prime of t, which is equal to 2i e to the power of it with an interval of 3 pi over 2 to 0. Okay, so yeah. Okay, so we will have the integral of 3 pi over 2 to 0, then negative 2 times e to the power of it, so multiply siya, distribute lang, times times plus 4 I e to the power of 2it. Then yeah, don't forget to write the dt. Okay, so by integrating this one, each expression nato siyang i-integrate, these two expression with respect to t. So we will have 2i times e to the power of it plus 2 e to the power of 2it, then integrate that one from 3 pi over 2 to 0. So we will have 2i minus e to the power, 2 times e to the power of 0 plus 2 times e to the power of 0, okay, minus we will have 2i e to the power of I 3 pi over 2, then plus 2e to the power of I, then times 3 pi over 2. This one is equal to negative 1, and this one is equal to 1. So therefore we have 2i times e to the power of 0 plus 2 times e to the power of 0 times minus negative 2 plus 2. Okay, so we have equal to, so it become, this one will become 0. So therefore we have 2i, then 2i, the is 1, so we have 2i plus